Alright, hell yeah. So we just spent probably an hour, not an hour, but it was ridiculous going through this, where this could be just so easy if you know the equations, but we did so just from the technical standpoint so you can see that afterwards. We have some sort of velocity coming in. We have a rolling disk. So this is going to have kinetic energy of translational motion and rotational motion. Hell yeah. And it has, we're setting this as our datum, so it has no potential energy, or the potential energy is 0. So that's going to equal up here, there's no energy lost from the system. It's just changed from kinetic to potential. None is due to friction or heat. And so what we have up here is we have no kinetic energy whatsoever. The thing has stopped rotating and it has stopped translating upward, right? And so we just have potential energy up there. So kinetic energy translational is 1/2 mv squared, sweet. And then kinetic energy is 1/2, what the hell, is it I omega squared? Hell yeah. And in the video we showed that these units are the same. If you've ever forgotten this one, you can use the units to kind of remember it or not mess up. Potential energy is mgh. Okay, so do we have anything similar? Well, sure, because I is going to be 1/2 mr squared for a disk. So let's throw that in. And these 1/2s are going to combine to 1/4. I'm going to do that all at the same time. So we have 1/2 mv squared plus 1/4 mr squared, and then we have omega squared is equal to mgh. Okay, so we have an m everywhere. We can cancel that, and then we know that they want it in terms of velocity. So radians times radius is tangential velocity. I like to say radians times radius is something normal. So also if we have, we could say that tangential velocity, there's something normal, do something weird to it, divide by radius is radians per second. So we can actually sub this into here, which we will. So we're gonna let's simplify this. 1/2 v squared plus 1/4 r squared. We're gonna throw this. So what's omega squared? That's velocity squared radius squared. Sweet. So we're gonna have velocity squared radius squared. These radiuses are gonna cancel. That's gonna be equal to gh. All right, sweet. So we have this v squared. So we can factor that out. We're gonna have 1/2 plus 1/4 is equal to gh. Hell yeah. So now we're going to have v squared, 1/2 plus 1/4. Maybe you don't know how to do that, but this is 2/4 plus 1/4. That's going to be 3/4. And right now you'd be like, oh, hell yeah, it's going to be that one, right? And so we got gh. So we're going to take this to the other side. You're going to have v squared is equal to 4/3 gh. And then v is the square root of 4/3 gh. And whoa. No. They just want the height in terms of v. Oh, what the hell are we even solving for? They want to solve for height. So we're saying height is v squared divided by g, and then 4/3. You know what I mean? Or height is 4/3 v squared divided by g. And sorry for the sloppy handwriting, but hell yeah, we did it. And for sure, that was under 5 minutes. So hell yeah, I'm going to start the video with this. And then you can see what we do. We do some pretty cool stuff. I think it's, it's kind of proofy. But it's just kind of a... Anyway, there you go. Alright, hell yeah. So this is rotational questions on the JEE. And so these are probably more simple ones. I don't know if they're simple or not. But anyway, so we have a disk of radius r, mass m, rolling up a horizontal without slipping with a speed of v right here. And then it moves up an inclined slope to a maximum height. So, So this is why we're doing rolling stuff, because we start out just with a point particle. So if we have a point particle with a velocity, hey, we have some sort of kinetic energy, and energy is just the easiest way to go, but it might not be visually representative. Sometimes it's hard to visualize what the hell's happening, but if we have 1/2 mv squared, this is the energy right here, and then at the height, hey, we don't have, well, we have two parts of energy. We have a potential energy And we still have kinetic energy, just like we have potential energy down here. But if we set our datum of 0, hey, we have 0 height. So this is mgh, and we have mg at 0. We have 0 height. Up here, we have that final height. That's kind of what we're interested in. And this is where it comes to a stop. So our velocity is 0. So heck yeah. So our kinetic energy, so we're going to have mgh plus 1/2 mv squared for our two types of energies, let's say. But this velocity is 0. So we just have, in this case, mgh. So then, basically, just common energy is the energy at this point. Energy can't be created nor destroyed. I don't know, but it can be transferred. It can be transferred through the friction in the air, through friction on the surface. But this is the ideal, where you have a frictionless frictionless slopes and frictionless surface with a point particle, and at some point, because of the force of gravity, is going to reduce this mass, because we still have a mass here. It's still maybe 1 kilogram, let's say, and it's going to only reach a certain height. And so that height is when 1/2 mv squared is equal to mgh. So this is kind of classic. Hey, the masses cancel. You can bring the 2 to the other side. That's v squared is 2gh. And then hell yeah, you get the kind of the classic is, and you should always just kind of, I don't know, more or less know where this comes from every time you see v is the square root of 2gh. Okay, so, but what we're going to say with rotation, now I got to pause the camera just for a sec. Holy Toledo. Oh, this is very fascinating. I got tripped out. I just turned the camera off for a second, but now I don't know. I hate when in physics you get to the point where it's just well, is this thing going to go higher than a point particle? Because it has more rotational energy. Yeah, that's fascinating. That's kind of fascinating to me. But what we do know is just kind of, I actually solved this one kind of easy from the opposite perspective. I like doing the vertical slope. You can do this kind of slope, and hey, you have a disk rolling down a slope, and you're going to get two things. When it gets, to this position, it's going to have transitional. It could be, it has a velocity, let's say 0 here, and then if this is your datum 0 and this is your height, then you have a potential energy up here of mgh, and then you have no potential down here. You just have all kinetic energy, and that's going to be 1/2 mv squared. But that's if it's a point particle. And so, yeah, from this perspective, I get what's going on, because you only have the force of gravity. I like to do this example of, if you just have a 1 kilogram mass and you drop it off a cliff, in 1 second, it's going to go from 0 to 10 meters per second, average velocity of 5. That means in that 1 second, it's going to go 5 meters. Sweet. It can't do anything more than that. This is basically what F equals ma says. If we have a mass, if we apply a force, it can only change it can only change its velocity by these known quantities. So if we apply this number for the force on this number of a mass, it can change its velocity by this number. You know what I mean? This continuity can't be kind of broken, let's say. And but what we see when we have something rolling down a slope, you should visualize it like this. It's not just dropping a mass off a cliff. It's also, we're going to do a little pulley here. It's also connecting this mass to another chunk of mass that's moving. So you have a driving force of, let's say, 10 newtons, because this is 1 kilogram, and that's going to be mg, right? But now, when it travels, let's say it does. Let's say it goes 5 meters. Okay, but it also pulled this one 5 meters. So now you have a total of 2 kilograms that just moved 5 meters in 1 second. You know what I mean? So that's the data that we just said. Now, what's the force required? That's kind of the end all. It's what is the force required to do that? And so if we said in 1 second both these travel 5 meters, you just work backwards, and it's a good strategy. That means they must have both had an average velocity of 5 meters per second, but they both have 0 velocity right at the beginning. So the only way to get an average velocity of 5 meters per second after a second is to have the velocity at 1 second to be 10. So this has got to be 10 meters per second, and this has got to be 10 meters per second. That means both these masses have changed their velocity by 10 meters per second, which is the definition of acceleration: change in velocity, change in time. And so we have F is equal to 2 kilograms times 10 meters per second squared. And this would require a force of 20 newtons, which we don't have. We can see that only 10 newtons is driving this whole system, because this is the only thing, subject to the force of gravity that can actually act in this direction. This normal force, you do have 10 newtons down, but you got 10 newtons pushing back up on the normal force, and that's going to be no net change of motion in the y direction due to that one. Okay, so the same thing is going on here, and I guess the short of it is that, this always trips me out, is, the force of gravity. That's why I don't like to do this. Let's do this one. So if we have a vertical slope. We have a disc rolling down a vertical slope. Now, maybe this is like gears or something, so it can't slip. But yeah, that's what we're saying, is it can't slip. And the only force on this thing is mg, is gravity. So if this is 1 kilogram, this is going to be 10 newtons. And what happens, and the thing that I like to do is, like, don't think this of as a disc. Actually simplify the problem and turn it into a hoop. And if you turn it into a hoop, all the mass is on the outer perimeter. And so what happens when we actually, when we drop this thing 5 meters, 2 things happen. One is that all the molecules, basically just go down here, and so we can say that. But this is the idea that 2 things happen. You have transitional motion, and then you have rotational motion, and both add up. And so if we're talking about kinetic energy, the kinetic energy of this point particle, sure, is just, the transitional velocity transitional, mass, and then 1/2, you know what I mean? Well, that velocity squared. Anyway, it's this. But when we talk about rotation, well, now, and let's do the ideal of just like a hoop. You have all this mass rotating on the around. So what we're gonna say is, like, check this out. So if this rolls 5 meters, every point on this actually travels 5 meters. And that's something that I can't really prove right. I'll try to get better, you know what I mean? But some things I just have to, like, kind of know that they're true, and then just get on with life, and then make those proof videos later. But this is kind of just like a rolling, anything rolling is, if it rolls out a track of 5 meters, that means that every point on here also is 2 things. If it rolls out a track of 5 meters, this center of mass moves 5 meters, so that's the transitional. So we have the check on 5 meters there. But if we roll out 5 meters, and this is where you actually, like, kind of put a little observer, like, right on here. The whole thing would look like it's spinning around you, and so every molecule on here is spinning 5 meters to go that distance. So it also has another 5 meters. All right, sweet. So that's the same thing as, so in this case, this did not jive, remember? Because we said we only had a 10 Newton mass, and we couldn't go 5 meters. So same thing here. If we have a 10 Newton force, and this transitionally goes 5 meters, but then all this mass on the perimeter also moves 5 meters, well, you can't have that. So is totally synonymous with this situation, where what is the difference? Do you think the distance is just 2.5 meters? Well, let's try that out. So in 1 second, if we travel 2.5 meters, because we only have 10 newtons of force, Okay, so our average speed is 2.5. Our max speed must be 5 meters per second. Sweet. So we have F equals ma. We want to figure out the force. We have 2 kilograms that are accelerating up to 5 meters per second squared. And hell yeah, that's going to take a force of 10 newtons, which is what we have. So in this case, this thing can only go 2.5 meters. And what we do is we compare it to free fall. You know what I mean? That's why you compare it to G. You know what I mean? Down here. So you have... if something's in free fall, hell yeah, in 1 second it's going to go 5 meters. In another second it's going to go another 15 meters. You know what I mean? And should we actually do that one? Because, yeah, we got 10 meters per second there. And then this, after 2 seconds, because of acceleration is 10 meters per second, our velocity is going to be 20 meters per second. So in this second, our average velocity was 15 meters per second, so we traveled 15 meters. So we're at a total distance of 20 meters away. Sweet. So that's if, but yeah, in this case, we're actually, you know what I mean, we only have this 10 Newton force, but the second this thing moves, 2.5 meters, this mass moved 2.5 meters too. This mass, this 1 kilogram, did 2 different things. Yeah. So it's fascinating. So instead of just this thing falling 5 meters, if for whatever reason, if this thing goes 5 meters, it actually went 10 meters. You know what I mean? Because I don't know. It almost seems fictitious, but no. It's like, hey, this outer perimeter had to spin, and so it went. So the whole system just went 5 meters, but this outer portion of the cylinder also went another 5 meters, and so it's basically like 1 kilogram going 10 meters. And to do that, 1 kilogram going 10 meters, again, average velocity would have to be 10 meters per second. If it starts out at 0, that would require an acceleration of 20, and then it's a 1 kilogram, so F equals ma, and we would have a force of 20 newtons, which we don't have. We just have, that's the thing. So that's the take-home message. If you have gravity acting on, you know what I mean, on this mass, you only have 10 newtons of force. That's kind of my take-home message. Is just like, that's all you have to work with, and so that. And so, what I wanted to, that's what I was comparing it to. In free fall, you go 5 meters. Our system only goes 2.5 meters. And so, 2.5. So that's going to be half of g. So if we say, hey, what's the acceleration? Well, it's just going to be 1/2 g. And this is for a hoop. You know what I mean? But we know that for a disc, and if you run it, it's 2/3. It's 2/3 g, because most of the mass is kind of around the center, which doesn't spin, and so you can actually have it fall faster, because when it does go, let's say 3.3 meters, all the other molecules, you know what I mean, they made up to that 5 meters total, and then so that 10 newtons allowed that to go 5 meters. Alright, hell yeah. So I took a huge break. I had to do some plumbing. Man. But anyway, so I'm back, and then I got to think about something. It's so fascinating. Like, I can definitely always imagine something with 0 velocity and requiring, like, a gravitational force of 10 newtons to get it up to speed after 1 second, you know what I mean? But I never think of the opposite. Hey, if I have something that's going 10 meters per second and I need to bring it to a stop in a time of 1 second, now you don't have to think about it in a time of 1 second, but well, it is useful because in this scenario, the force is going to be the same as gravity. I must put a force on this to slow it down, and that force is going to take 10 newtons. Now, the same thing is true with a rolling wheel, because if this is the hoop that's rolling and it's up to speed, and then in the next second I want to bring it to a dead stop, well, not only is its transitional motion, you know what I mean, that's why they call the center of mass. I have to like slow that down, but then I have to also slow like the spinning stuff. So I just thought of this. This will be a pretty good analogy. So let's say we run this thing, And so after 1 second, this thing has fallen from here to there, and it's and in our case, it has fallen under gravity just 2.5 meters. We've already said that. And then it's pulled along this thing to there. And so both these things have a speed of 5 meters per second. And so what we want to do is we want to slow this whole system down to a dead stop in 1 second. So in 1 second, we have to slow this down. And if we put a, let's see. Maybe I wanted to do the mainly more of the analogy of I guess we could do this. Yeah. So if I have to stop this thing, I only have to put a 5 Newton force. So even if this is 1 kilogram, it's only going 5 meters per second. I only need to change its velocity by 5. So the acceleration is only going to be 5. And F equals ma says I'm going to change the velocity by 5. It's a 1 kilogram mass. It's just going to take 5 newtons. So it's only going to take 5 newtons to slow this down. And when I do, hey, this string is just going to go slack, but this mass is still going to be continuing moving. And so I need to actually come up here and apply another 5 newtons and stop this chunk of mass. And if I do that, then I have applied 10 newtons, which is all I get. Gravity just gives me 10 newtons for this scenario. And I guess this probably isn't the best analogy, because here I have a 1 kilogram mass, but as it's rolling, we're saying like, whoa, like it's the same 1 kilogram, but that 1 kilogram is moving this way, let's say at 5 meters, but then it's like spinning around itself, and it has this rotational distance that it's traveling another 5 meters. So so that's kind of what's happening there. And all right, hell yeah. So hopefully all that's decent. But anyway, we don't have a hoop. A hoop is perfect because when a hoop rolls down a vertical slope, it doesn't fall at gravity, it falls at half. But when a disc rolls down a slope, it's going to fall at 2/3 gravity. And then the same thing is true when the height. So when a disc rolls up a hill, you still only have this 10 newtons of you know what I mean? Or like let's say this starts to roll up a vertical slope, so it just instantly rounds a corner and now it's going up vertically. Well, gravity will provide a 10 Newton force because this is a 1 kilogram mass, and that's the only force that it can provide. And if that's the case, hey, this thing can only be traveling this direction. Let's say it's a hoop again, it can only be traveling this direction at 5 meters per second, because 5 newtons are going to be required to slow this down. Again, we said here 5 newtons was required to bring this motion to a stop, but it's still rotating. So another 5 newtons is going to be out of this 10 Newton gravitational force is going to be used to bring that rotation to a stop. And that rotation, if it is a hoop, you have things that are moving 5 meters per second with tangential velocity. So you actually have to bring those to a stop. And we're going to say that we're going to do that all in 1 second. So we're going to bring this motion to a stop. So once it rounds this corner, hey, it's got 5 meters per second upward, and in 1 second we're going to bring that motion, that transitional motion, to a stop, and its rotational motion to a stop. And so in this scenario, let's see what happens. The max height, and how would you compare this? Man, I'm tripping out because I feel like this is a weird comparison. But if we have a point particle that doesn't rotate and it has a speed of, let's just say it has the same speed of 5 meters per second. Well, we can do that a whole of a hell lot faster than a second. So with a point particle, we can have a speed of 10 meters per second, and we're going to stop that 1 kilogram point particle in 1 second. So that thing will have a height of 10. Now this thing will only reach a height of 5. So that's kind of the question. What height will this actually reach? And if the velocity is 10 meters per second and it's a point particle, it can reach a height of 5 meters. Yeah. But because if it was a rolling hoop, and that's the only thing with the numbers. If it was a rolling hoop, it has a speed of 5 meters per second, and then it goes to a speed of 0 in 1 second. So it can only reach a height of 2.5 meters because its velocity is 5 and its velocity here is 0. The average velocity is 2.5 and it went a second, so that's 2.5 meters in height. And so if it's a disk, it's going to be somewhere in between there. And so all right, hell yeah. So let's just guess, and I would assume like 6.6 or 10 divided by 3 is is 20 divided by 3. 6.6 would be the speed incoming of a disk that would probably satisfy. So we're going to say at 6.6 meters per second, that's going to stop, and then so we would have a average velocity of 3.3, and so that would be our average velocity for 1 second. So that's going to be our height. Our height would be 3.3, I think, for a rolling disk. And then which of these would make the most sense? So we have a incoming velocity of 20 divided by 3. We're going to square that, and then we're going to divide by gravity. And so that's going to be a height of 4.4 for that one. We only see a height of 3.3. So I'm going to store this as x because it's going to be some fraction of this. So how about 0.75x? Heck yeah. So it looks like it's going to be that one. And now we're going to see if we could get there just from an easier perspective. But I think that was decent. I could probably clean up my words just a whole lot better. But that was a pretty good analogy. It's not even an analogy. It's like literally what's happening. Gravity is the only force that can stop motion. And if you're stopping transitional motion, at the same time you're stopping rotational motion. So, you only have this much force to do that. Okay, but hell yeah. So let's see if we can actually do the quick answer. Yeah, I thought I did this once, and so yeah, let's figure this out. So we have a potential energy. How would they solve it? You know what I mean? They would say that you have, let's see, you have some sort of kinetic energy here, and you have kinetic energy from rotation and translation. So kinetic energy from rotation and translation, so we already kind of figured that. And then once you get up to here, you have no kinetic energy. It's stopped rotating and it's stopped translating, and you only have the potential energy. But those are equal to each other. So if it didn't have any rotation, you know what I mean, that's where we just said 1/2 mv squared was equal to mgh. Yeah, so it's fascinating because I didn't want to do the equation for kinetic energy of rotation, even though I did kind of memorize it now, or I saw it once, and it was just the other day. I tried not to use the equations as much as possible because especially the work equations, just trying to use Newton's laws of motion, just because you can get a better fundamental understanding of what's going on. It's going to be a bizarre and harder way to get there, but it's still, because what is this? This is going to be, is it just I omega squared? Is that what the kinetic energy is? And we could figure this out because the units are the equations. So this is going to be 1/2 mv squared. So this is going to be kilograms, meters squared, seconds squared. So let's figure out what this is. I is mr squared. it's mass times the distance squared. That's the definition of mass moment of inertia. Sweet. So we have, so this is going to be kilograms, and then we have meters squared, and then this is radians. So a radian per second is what omega is. And then radians is dimensionless. So this is just really just 1 divided by second. And if we square that, hell yeah. All right, so heck yeah. There's a check on reality that I did a pretty good job of memorizing that. Okay, and then for a disk, I is just 1/2 mr squared. For a hoop, it just makes sense that all your mass is out on the perimeter. And, if we just have a string and a mass on a string and we're spinning it around, and this is 1 kilogram and this is 1 meter, well, the definition of mass moment of inertia, or the second moment of mass, it says, hey, we have a mass out here. Okay, cool, we have 1 kilogram, and it's a distance of 1 meter away. And now this would be the first moment of mass, just like we have a first moment of force. If we put a force out here and it's a distance there, heck yeah, the moment is just force times distance. But this second moment of mass term, or moment of inertia, is the second moment of mass. So we say that it's the mass times the distance to the mass, but squared. So sometimes you see it as like that, especially in parallel axis. You'll be like, yeah, this is your common definition for mass distance squared. Cool. All right, so for a hoop, it's all at the perimeter, and then so you're just summing all these forces. So I mean all these masses. So it's just mr squared for the individual. So it would be, if you had 10 of these masses, well, you'd have m divided by 10 r squared, and then you would just add them all up, and then they would add up to mr squared. All right, so hell yeah. And then for a disk, you don't have your masses out at the perimeter, and so you have a lot of your masses are close to the center, and then the distance squared is just much smaller. So instead of for a hoop, which is mr squared, you have 1/2. And you would probably, I don't know if there's any quick proof besides, like, I don't know, just throwing this into Excel and then picking chopping this up, into a finite little chunks of mass, and then picking their distance, and then summing those all up, and then you will just get this. I would like to find ways to actually do it faster, to see it, just even in a couple steps, see it approach 1/2. But hell yeah. Okay, so booyah. So this is, yeah, I don't know why I don't want to. I thought I solved this from the perspective. Oh yeah. So I solved it from the other perspective. So if I do have a disk that's rolling down the hill, yeah, this is a good. I mean, because this is the problem that you want to be able to just solve real fast. So we have some sort of tension here, because either the disk is spun up with string and then it's rolling down, like rolling down a vertical slope is the same thing with a disk that's bound up with string, and then you're just holding it and then it's rolling down the string. That's going to be the same. And then so here's your equations, is that you sum the forces in the y. So you have mg, we're going to say this is the positive direction, mg minus t. So this is basically, all right, hell yeah. So we use, where are we at? So we have F equals ma. So this is summing the forces in this direction, like let's say the y direction. And so we say we have mg, that's going to be positive. This is the opposite direction, negative. And that's going to equal our mass times the acceleration. And it's going to be this direction. This tension typically will always be less if you're just holding it, and obviously this thing's just going to unspool. We can do that by observation. That's what's going to happen. So that's the first equation. The second equation is sum of the torques is I alpha. And I have not derived this one. I need to read some more literature, because that's where I don't like to use this one yet, because I don't know, I don't mind using it. I just don't know where it comes from and stuff, from a fundamental perspective, and that drives me absolutely insane. So we take the torques about the origin because we want an equation with t in it because we have a t unknown right here. So we want two equations with things that are known, and then, we can only have two unknowns. So we're going to have acceleration unknown and then t unknown. So our torques from here, this is the distance r, so we have tr, that's the torque, right? This force times that distance. That's the first moment of force, right? And then we have I for a disk, that's 1/2 mr squared, and then alpha, I can do this real fast now. So I said, omega radians times radius is something normal. That would be tangential velocity. Same thing with alpha. Alpha, angular acceleration times radius is something normal. That's acceleration. So if I just think, hey, what's angular acceleration? Well, that's going to be something normal. We got to do something weird to it. We got to divide by the radius. Hell yeah. We take this radius to the other side. We'll have r squared up here. You see that? And then we can just cancel that r squared with that r squared. Hell yeah. And then so we'll have an equation for t that's 1/2 ma. That's it. And then so we throw that into here. So we have mg minus 1/2 ma is equal to ma. And then this is a half that will add to this side. So we'll have 1 plus a half, that's going to be 3/2 ma is equal to mg. The masses cancel, and then we just throw this 3/2 to the other side. We have acceleration as 2/3 g. Hell yeah. So that's just kind of like, this is a problem that you should just have in your pocketbook. You know what I mean? This would be the easiest, probably the easiest one to do. What this is saying is that under the force of gravity, this thing, because it's doing all those things, because it's not only every molecule is translating, but it also is rotating with the force, given of gravity, it can only have an acceleration of 2/3 g. So in 1 second, we're only going to have a change in velocity of 6.6 instead of 10 meters per second. Cool. So that means if in 1 second it can only go 3.3 meters. Cool. And so keep that in mind, because now if this thing is rolling up a hill and it has a speed of 6.6 meters per second, well, hell yeah, it's going to stop at 3.3. So that's kind of what I was getting at, is just like, hey, think of it in both directions. I think it's easier to think about it this way, like, hey, something's speeding up, but also if something is up to this speed of 6.6 meters per second, well, it's going to stop pretty fast, you know what I mean? It's going to stop only in 3.3 meters. Yeah. Alright, hell yeah. This is tripping me out, though, because you're just like, well, wouldn't it slow faster? But no, because it has a translational speed of 6.6 meters per second, which seems slow, so it seems like it would slow, like it would, oh, yeah, what, is this still going to take... Oh, this is fascinating. Okay, this is where I'm getting messed up. Is because it's still going to take a full second. It's still going to take 1 full second to slow this. That's the part where I'm getting mixed up. Because if I just have a point particle coming in at 6.6 meters per second, it's only going to take the 2/3 of a second to slow down. Because if it's 1 kilogram. So that's kind of like playing around with this. Is yeah, if I have a point particle coming in at 6.6, well, that's I can, in 1 second, I can slow a 1 kilogram mass by 10 meters per second. That's the acceleration of of gravity if it's going straight up. But what this says is like, hey, it's not a point particle going 6.6 because it has all this extra rotational energy, you know what I mean? Or just, and I don't like to think of it as energy. I like to think about it as actual particles that are moving. And so you have you have particles that are going to start moving this way, but also you have particles that are moving this way. And by having it roll up the slope, you know what I mean? As it slows down, it's going to do those two things at the same time. It's going to reduce its translational speed, as well as at the same time and in the same ratio reduce the, if it's like a hoop, you know what I mean, for sure, it's going to reduce its the speed of the particles on the outside of the hoop. Now a disk is it's a little bit more spread out, and that's why this isn't a half, and we just showed that. You know, from here it's only 3 halves. So this is a higher speed. So compared to a hoop, you're only falling at half of gravity, but because most of your mass is mainly translating and isn't really rotating, especially the mass around the center, hell yeah, your speed is faster for a disk when it free falls or unspools itself. It's closer to free fall than a hoop for sure. But I mean, it's not. I mean, you still have plenty of mass. You know what I mean? It's not like 0.8. It's only 0.6, and free fall is, or I'm sorry, it's 6.6. It's not 8 meters per second acceleration. It's 6.6, where gravity is 10, and a hoop is 5. So you know what I mean? It's not too much better than a hoop in free fall, but more of the mass is in the center, and so it's this force of gravity gets to move this direction without having to spin all that extra mass up to speed. And yeah, I think it's fascinating that, like, that's something that just seems bizarre. Like, I'll take it on faith until I can find kind of ways to prove from proofs that, like, hey, when a disk translates this way, it's also spinning, but those are like 2 separate motions. Like, every molecule is both going this way and spinning. Like, they're additive. There's nothing about that cancels itself out, which that's kind of the bizarre thing. It seems like it might, you know what I mean? It's not super intuitive that, like, it might cancel out, but I guess it doesn't. Alright, hell yeah. So I think I know where to go with this to kind of end this video. Is this idea that if we do have something in free fall, cool, we have the gravity's 10, you know, and so that's that G term. And if we run it for 1 second, it's going to have a distance of 5 meters. So how does that relate to gravity? Well, you can just kind of see, well, that's just going to be half. And, you know, don't get too confused, because if we run this for another second, we're always going to be like multiplying by the time to get position. So this position is going to be, that's why this position is 1/2 AT squared. This is the kinematic equation, but those are things that also you shouldn't memorize. You should just kind of like, I don't know. I mean, I'm just doing it how I do it. But then I always like to work backwards, and it's just like, well, how did I get this number? Well, just if I run it for 1 second, it looks like I just took gravity divided by 2. Sweet. But if I have a rolling disk, I can't go 5 meters. We said we could go 2/3 times 5. And so, if I took G divided by 2 to get this 5, or to get this height of dropping, let's say, which is the same thing as if it was up to that speed, that same speed, what would be the height after 1 second of slowing to a dead stop? This height was G divided by 2. But if it's a rolling disk, we would have G divided by 2 times 2/3. So we would actually have G divided by 3. That would be the height. And then this equation is kind of interesting because it also says, like, it also involves the velocity. So if we had, alright, I see where I just wanted to come up with this answer just from a unique way. And so I think I can. Because if we do have a rolling disk, I know that this just by definition is 2/3 G, and you should kind of memorize that. You know what I mean? You shouldn't have to even do whatever this one was. You know what I mean? Some of the forces, some of the torques to get there. We just know that that's the acceleration. So if we say that is the acceleration, that's going to be dv dt. You can separate variables and integrate. We get an equation for velocity. That's going to be 2/3 gt. Integrate again, we get position. And we have an initial velocity. In free fall, we have an initial velocity of 0. And then so our position is going to be 2/6 gt squared. I hope this is going to work. And what we would do is we would solve this equation for t. So we would have 3/2 velocity divided by g. And that's going to be t. Then we could square it. We're going to have 9/4 v squared g squared. And then we'll throw it into here. So we have a position of, which would be our height. Same thing, like you could either run it for 0 velocity going to here, or you could run it in the opposite direction. I think that would be the same. Maybe, hopefully it is. Alright, so we're going to have 2/6 g times 9/4 v squared g squared. Oh, I feel like I messed this up. Oh, yeah. Oh, bummer. Oh, no, never mind. This G just looks like it's downstairs. It's not. It's upstairs. So this G is going to cancel one of those. And hey, that cancels. This becomes a 2. This will become a 2, and this will become a 3. So we have 3/4. So we have 3/4 v squared g. Okay, hell yeah. And that's the same answer. 3/4 v squared g. So you could think of it like that. And I think that's how I solved the problem initially. I was just like, oh, well, isn't acceleration just 2/3 g? So then I can actually figure out the height. I don't know. Yeah, it was kind of interesting. And I guess I'm running it this way for a second, which is the same thing as running it the other way. Cool. All right, so I guess now we should just do it official. So let me grab some more sheets of paper. Alright, hell yeah. And I think if we just use the kinetic energy equations, we can get there so fast and so easy that I'm going to put this at the end and at the beginning. So I'm going to start the video kind of from here. Here we go. Alright, hell yeah. So we just spent probably an hour, not an hour, but it was ridiculous going through this. Where this could be just so easy if you know the equations, but we did so just from the technical standpoint so you can see that afterwards. We have some sort of velocity coming in. We have a rolling disk. So this is going to have kinetic energy of translational motion and rotational motion. Hell yeah. And it has, we're setting this as our datum, so it has no potential energy, or the potential energy is 0. So that's going to equal up here, there's no energy lost from the system. It's just changed from kinetic to potential. None is due to friction or heat. And so what we have up here is we have no kinetic energy whatsoever. The thing has stopped rotating and it has stopped translating upward, right? And so we just have potential energy up there. So kinetic energy translational is 1/2 mv squared, sweet. And then kinetic energy is 1/2, what the hell, is it I omega squared? Hell yeah. And in the video we showed that these units are the same. If you've ever forgotten this one, you can use the units to kind of remember it or not mess up. Potential energy is mgh. Okay, so do we have anything similar? Well, sure, because I is going to be 1/2 mr squared for a disk. So let's throw that in. And these 1/2s are going to combine to 1/4. I'm going to do that all at the same time. So we have 1/2 mv squared plus 1/4 mr squared. And then we have omega squared is equal to mgh. Okay, so we have an m everywhere. We can cancel that. And then we know that they want it in terms of velocity. So radians times radius is tangential velocity. I like to say radians times radius is something normal. So also if we have we could say that tangential velocity, the something normal, do something weird to it, divide by radius, is radians per second. So we can actually sub this into here, which we will. So we're gonna, let's simplify this. 1/2 v squared plus 1/4 r squared. We're gonna throw this. So what's omega squared? That's velocity squared radius squared. Sweet. So we're gonna have velocity squared radius squared. These radiuses are gonna cancel. That's gonna be equal to gh. All right, sweet. So we have this v squared. So we can factor that out. We're gonna have 1/2 plus 1/4 is equal to gh. Hell yeah. So now we're going to have v squared. 1/2 plus 1/4. Maybe you don't know how to do that, but this is 2/4 plus 1/4. That's going to be 3/4. And right now you'd be like, oh, hell yeah, it's going to be that one, right? And so we got gh. So we're going to take this to the other side. You're going to have v squared is equal to 4/3 gh. And then v is the square root of 4/3 gh. And whoa. No. They just want the height in terms of v. Oh, what the hell are we even solving for? They want to solve for height. So we're saying height is v squared divided by g, and then 4/3. You know what I mean? Or height is 4/3 v squared divided by g. And sorry for the sloppy handwriting, but hell yeah, we did it. And for sure, that was under 5 minutes. So hell yeah, I'm going to start the video with this. And then you can see what we do. We do some pretty cool stuff. I think it's, it's kind of proofy. But it's just kind of a cool... Anyway, there you go.